When dealing with waves and oscillations, it's really useful sometimes to use complex exponential notation, which means we're going to be using Euler's formula and converting between complex exponential notation and sinusoidal functions. So just to refresh our memories about how this works, the square root of -1 we call I, so that I squared is equal to -1. And these are the imaginary numbers. And so some incredible things are true when we have imaginary numbers, in particular Euler's formula, that says that the complex exponential e to the I times theta is equal to the sum of cos theta and I times sine theta. You can prove this actually relatively easily by doing a Taylor expansion of this exponential function, and then you find that you have terms that are real, giving you the Taylor expansion of the cosine function, and the imaginary terms giving you the expansion of the sine function. If we make theta equal to pi, then we get something called Euler's identity, which says that e to the I pi plus 1 is equal to 0. And this was once described by Richard Feynman as the most remarkable formula in mathematics. Now we can represent complex numbers on a two-dimensional plane where the horizontal axis is real and the vertical axis is imaginary. And so we can say that the horizontal component of some phasor, some vector, if you like, with length r, the horizontal component is given by r times cosine theta, and the vertical component is given by r times sine theta. Or in terms of complex numbers, the x component in the horizontal direction is the real part of r times e to the I theta, and the y component is the imaginary part of r times e to the I theta. Now, if we allow this phasor, this vector, this red arrow here, to rotate around in the complex plane, increasing its angle theta, and we look at the height of the vertical component, we get an animation like this. And we see that as the thing rotates at constant speed, as we plot out the angle of rotation on this axis here and the height on the vertical axis, we get a sine function. So this is a projection of the vertical component of this phasor as we increase the angle theta. If we were to project the horizontal component in this direction down here, then we would get a cosine wave. So to summarize, if you collapse uniform circular motion to one axis, you get a sine wave or a cosine wave, depending which way you project it. And the red arrow we call a phasor, and the angle of the phasor can be used to specify a point in the sine wave, because it's the angle of this phasor that we are speaking of when we think about the phase of a sine or cosine function. It will come up in this course that we end up having to convert between complex exponential and sinusoidal representation, and I want to give a couple of instructive and useful examples of how this works. So here is a sum of two complex exponentials. You'll notice the second term here, though, is the complex conjugate of the first, which means that if we expand these in terms of sine and cosine functions, we should see some cancellation, and hopefully all the imaginary parts will cancel out. So let's do that, and we see that we have, so the curly r here represents the real part, curly I is the imaginary part, and we see that these two imaginary terms cancel, and these two imaginary terms cancel, leaving us only with real valued functions. Collecting the terms, we see that we have a cosine function with an amplitude of twice the real part of b, and a sine function with an amplitude of -2 times the imaginary part of b. Now, we could still contract this further by writing it as a single cosine function with some amplitude a and some phase phi. But what are a and phi? Well, there are a couple of ways of doing this. One way is to use brute force and trigonometric identities. So let's use this trig ID here, which is going to contract this product of cosines and sines subtracted into a single cosine function. We'll obviously replace alpha with phi and beta with omega t, and which means that we should be able to write a cos omega t plus phi as this difference in sine and cosine products here. This means that according to this, what we're trying to contract here, b1 must be equal to a cosine phi, and b2 must be equal to negative a times sine phi. And in this case then, this expression here will be the same as this expression here. So now we need to solve for a and phi. Well, we can take the square of these equations, 1 and 2, which gives us that b1 squared plus b2 squared must be equal to a squared. And we can divide these two equations to find that the tan of phi must be equal to negative b2 on b1. Note that you still have to take care of which quadrant this is in, so it's important to know which one has the negative sign here. Now, that works fine, and so we've converted here a sum of cosine and sine into a single function, but there's a better way of doing it, thinking about the complex numbers and phasors. So here again is the thing we're trying to convert. We can rewrite this as the real part of these complex exponentials, and we can take out a factor of e to the I omega t, and we can convert this b1 minus I b2 into a single complex number in polar form, and then we can draw it. So here is b1, and here is I b2, so that's in the complex plane, and it's in the negative direction. And then here's the total amplitude A, and the angle phi. So then we get, as before, that the sum of the squares of b1 and b2 is equal to a squared, and we see that the tan of phi is equal to negative b2 on b1, but this will also make sure we find the right quadrant. So we won't be, if the inverse tan of phi isn't unique because we don't know whether b1 or b2 is negative. So this is a great way to get the correct quadrant of phi. So to summarize, Euler's formula allows us to replace sine and cosine functions with complex exponentials and vice versa. It might seem pointless at times, but as I've hoped I've demonstrated with an example using a phasor diagram, you can avoid using trigonometric identities sometimes, and that can make your life easier and avoid mistakes. So that's Euler's formula, and that allows us to write, for example, cosine omega t as the real part of the complex exponential and sine omega t as the imaginary part of the complex exponential. And we're going to see omega t's popping up a lot in this course. Omega is the angular frequency and t is time. And what it means is when we have equations with omega t's in them, instead of using sine and cosine omega t, we can work with just e to the I omega t. We can do all our algebra using that complex exponential, and then it's fine just to take the real part at the end. And in this way, a lot of algebra can become easier, and we can use some phasor representations, and we'll see how that works when we get to doing some of the physics a bit later on.